So hello, I'm going to go through today some of the workflows for oligonucleotide analysis. I will be handing over to John Fox at some point, although I was going to go through the full presentation. I'm going to have to run at some point, unfortunately, due to schools. So I'll get started. So I think we all know that the oligonucleotide market has seen an explosion recently. There's just a few statistics here with 5 new oligotherapeutics reaching the market at a huge cost there. And there's over 135 oligos in clinical trials currently. And I think we're all very aware of this COVID-19 pandemic and the increase in analysis requests being made because of this. And in the news recently as well, we're seeing test kits being recalled through contaminations. So I think it highlights the importance of having robust and validated oligo testing methods. Oligos, as much as we love oligos, they aren't the easiest of things to analyse. There's various analytical challenges when we're looking at oligonucleotides. There can be singly or doubly stranded. We're dealing with a wide range of molecular weights and sizes. We're also looking at these high number of negative charges that they pick up. There's diastereoisomers. You've got various modifications, not just of the backbone, but of the sugar, of the bases themselves. Certainly for therapeutics, where what we really don't want is the body chopping up our therapeutic and digesting it and using it as food. So these modifications designed to make that not happen. We can, when we're looking at LCMS, we can certainly start looking at some more specific analytical challenges that we're all facing whilst analysing these compounds. And I think certainly a big challenge at the moment is the identification of these co-eluting impurities. There are many impurities, N-1s, and so on and so forth. These are large molecules. So at Waters, we're very aware of this challenge, and we know that a requirement really is this accurate deconvolution. Can we accurately deconvolute? And not only deconvolute, but can we do it across a wide spectral dynamic range? So at Waters, the solution for us has been we do also have MaxEnt, but also to look at this new deconvolution algorithm called base spray. And what we're finding is that it's far better suited for the deconvolution of oligonucleotides. So we're getting far better mass accuracies. Another challenge that we're very aware of is the mobile phase additives. Not only their stability, things like HFIP go off very quickly. There's results out there showing differences and variations in stability over a 12-hour period. And we also know they're really expensive. So if you're doing QC type analyses and you're running high throughput analyses, it's the cost per sample. So what we have done and looked at Waters is to validate some methods using different concentrations of these mobile phase additives. And we've also done it across multiple labs. And we do have validated methods for this. So if this is something that anybody's interested in, please do get in contact with us about that. And going back to this idea of the impurities and these co-eluting impurities, we know we need to identify at sub-5 Dalton mass differences. And the problem we have is that we're having to try and differentiate between overlapping isotope patterns. Now, for us at Waters, we're fortunate we have eye mobility devices, and there has been some work done recently by D. Fabrice at the University of Connecticut, where he was looking at resolving post-translational modifications, employing the cyclic IMS, and they've got really decent resolution here. So something that you can't necessarily do with chromatography and mass spec alone, but when you pull in the eye mobility, we're getting that resolution there. So at Waters, I just want to take you through kind of some of our solutions, because we have the software, the separation and your detection side of things. So we're using Unify here, Unify being it's compliant ready, and it is very much workflow driven. We have intelligent automation when we start looking at unifying some of our compliance systems. So what that means is we have automated system setups and automatic calibrations. You can press a button and off it'll go and do all these things for you. Detector setups, everything. It's incredibly user-friendly. It will automatically do data acquisition. We can have our Unify giving us automatic purity calculations, automatic reports. We can use custom calculations, automatic deconvolution. And I think it's worth noting the Waters investment at the moment, not just in technology, but in application software within the oligo area. And that is ongoing at Waters as well. So Waters Connect is our new software platform. This is how it looks. This is the Waters hub. Unify's there. It's exactly the same as other Unify. There's just been some added benefits for oligo analysis, which I'll go through now. So what's new in Unify in Waters Connect? Well, you can enter target masses now into the component tables. You have what we were saying there, which is our base spray deconvolution algorithms. You still have Maxent as well. And we also have over here, when we're looking at selecting the molecule type, is that you don't just have to select protein or oligo now. You can also select the phosphothiolated oligo, so that PS backbone. And what we find is that the model deconvolutes far better. So that's kind of some of our new things and new additions to our software. But if we look at our solutions for oligos, obviously we have our separations. So you have your LC systems. We have our columns, which are oligonucleotide columns, which I'll talk about briefly in a little while as well. And we also have this mass prep standard. When we then come across into our detection, for the more QC analysis, we have our QDA and SQD systems. So asking the question of, have I made what I've wanted to make? And then when we start coming further down that list and start looking at characterization, we have Xevo, and we also have our Vion, which is our top instrument with eye mobility in. We then also have our biorecord system, which is what I'm really going to focus on today. And we also have our characterization of our more research level instrumentation with the cyclic and our Synapt XS. So this is our oligo technology. These are our oligo columns. They've got a wide pH range. They're stable across quite a large temperature range as well. And we also have this mass prep standard. So this basically consists of 5 oligonucleotides, all thymine bases, ranging from 15 to 30 base lengths. And we run it as a quality control in our analyses. We spoke briefly about the cost of these ion pairing reagents. These are, I've just put together a kind of group of commonly used ones. At Waters, we've kind of concentrated on the TA-HFIP system. And as I said before, we're getting down to the 80 millimolar for the HFIP. And we're happy to share some of our validated methods for that. So as I said, we're going to concentrate on the biorecord today mainly. So this is the biorecord system. This is a TOF system. I'm always amazed that there's actually a time of flight in that device. It's actually slightly smaller than the LC stack. It's compact, it is robust. I've got some data on the robustness that I'll show you shortly. It is workflow driven, it's completely compliant. And there's a button on the front of that panel which is just pushes it on and off. It's on-off start. It will completely automatically set up for you. So we did check the robustness of the biorecord for oligos, and this is just some of those results. So we basically just did 100 and 600 batch injection of our OST standard, so that 5 component standard. And you can see there in the bottom left hand corner where we've overlaid injection 13 and injection 600 that we're getting consistent retention times the peak resolution is consistent, peak intensities are consistent. So I was really happy with those results, and I think it shows the robustness of this system. So in conclusion of the biorecord, I don't really want to spend a lot of time on instrumentation, but I just really want to get across really that how automated this setup is. I've worked with mass spec for a long time, and yeah, this is about as easy as it gets, I think. It really is designed so that you can spend more time looking at your results than troubleshooting a mass spectrometer. So I think it allows non-mass spectrometrists to access the information that can be provided. So we have set up some workflows here at Waters. So I just want to take you through some of our oligonucleotide workflows. So how we've set them up into 2 workflows. Workflow 1, and I think the goal there really is, have I made what I expected to make? We're looking at quick routine batch deconvolution, identification, and you can get MS purity calculations out of that. And we're sending all that straight to a report. So you can put your analysis on in the morning or in the evening, overnight, and in the morning you can have all your results straight in a report, and I will show you a report later. And our workflow 2 is more our characterization workflow. So we're looking at in-depth characterization of that oligo, the impurities, the sequencing of those. And we're also looking at those low-level impurities, and we're trying to target down to that 0.01% of the FLP. So workflow 1, have I made what I expected to make? So this is our first workflow. We can import target lists directly into the sample list for submission. We do have purity calculations. It's worth noting that actually most calculations you can do in Excel, you can actually get Unified to do in the custom calculations. So it's not just purity, you could have a variety of calculations there. And I think what's quite nice is if you're running a kind of 6 injections at the front end to check for reproducibility, you can also have all those calculations done within here as well. So this is how the simple sample list looks like. You can take your list of expected masses, you import them in here, you've got your tray there on the left, and then you literally can just press start and off it'll go and do its thing. This is how your initial results, your review panel looks like. So your workflow can be how you want it to be. You can have various workflows in here. You have your results here on the top where it's giving you your purity, your observed mass, your delta masses. You have your chromatogram here on the left, your deconvoluted spectrum and your raw spectrum. You'll also see there in the top left you have something called the investigative tab. Pardon me. And that's where you can go in and manually look at the data as well, should you want to. This is our automatically generated report. These are completely customizable. Anything you can do in that investigative tab where you're manually mining through that data, you can have in here. And we have it for this workflow is we have a list of past oligos that have passed based upon a mass accuracy threshold. And we have a list of ones that have failed. And you can also have in the chromatograms should you want to. So our workflow 2 is a little bit more of an in-depth workflow where we're looking at that characterization of our oligos. So the unified workflows can be created and they essentially are there to guide the user through a series of data review steps. So we have purity here, trend plots, different impurities we've pulled out, looking at our UV data, and the amount of customizable options here are quite vast. This is where we can add in our target regions if you don't want to just add in a list. These are base spray settings. It's worth noting that what we find is that up to about 20,000 Daltons, we can use the same set of parameters If you're in the same sample list, have got a 10 ma versus a 60 ma, we're starting to look at splitting some of these parameters up. But we do have a robust set of parameters that we're happy to provide that will work very well between a 1 ma and up to that 20,000 Dalton region. We also have our scientific libraries, and these are important for in-depth characterization because this is where we put in our modifications. So all the types of modifications that you can think of that you suspect may be there. And what the software will do is, based on mass, it will go out there and try and find them and list what it's found for you. So this is kind of a results view of that. And as you can see there in the table, it's listed here in decreasing intensity. You've got your responses, your observed mass, your expected masses, your ppm errors, and also you've got your modifiers, where it's believed that it's found the modifier. And I think it's just worth noting here as well, just as an example of a low-level component at the 0.4% of the target FLP, which can be identified down to that level with a 1.1 ppm error. And I think for the bioaccord system, I think this is really good. Yeah, really nice data. Again, you've got your chromatogram on the left and your deconvoluted spectra on the right. I'm not sure if anyone can hear me. I seem to have crashed.
There was some noise, but now it's good again.
Okay, I'm going to try and get it going again. Let me stop sharing and then try again.
Do you want me to take over?
I've crashed, John. Yes, please.
Okay, so this is the benefit of being in the office today.
Naughty Wi-Fi.
Okay. Can you see my screen now?
Yes.
Yes, it's working well. But John, there is a strange echo when you're speaking. I'm not sure whether you might have two microphones on.
I should. There shouldn't be. Still an echo?
Now it's better.
Okay, let's just skip to where Emma was up to. So yes, thanks for that, Emma. That was great so far, and I guess hopefully you can stay with us and not get cut off entirely. So Emma had got up to the sort of results view where we were showing we can identify sort of peaks across quite a wide dynamic intensity range and identify those modifications automatically. And also in Unify you can do additional plots such as trend plots for batch comparison or lab inter-lab sort of comparison or stability degradation studies. Another capability we have, which has been in quite high demand recently, is the sequencing for confirmation of oligonucleotides. And what we can do is acquire simultaneously fragmentation information on the bioaccord. So we'd record one trace with low energy and one trace with high energy. We can actually do it on all our systems, and we've been doing it on all of our systems for probably about 10 or 15 years now, quite a long time since, anyway, QTOF Ultima a long time ago. So it's something we're very, very used to dealing with, this type of data. And the benefit of this is we can get sequence information, we can get MSMS confirmation, it can help us localize the modifications or substitutions or impurities, and we get that as free at the same time as we run our data, so you don't need to go back and reanalyze the samples or run any targeted MSMS And this is just an example of how the processing of that looks. So you can paste in your sequence and the Spectrum Tool software will automatically match all of those fragments. And you can choose which ion series you want to match. So for the visualization purposes here, we've just matched the most intense W series and the A-B series, but you can match other series as well, which is especially useful if you have different modifications on your oligo, because there you will get different fragmentation series being the major ions. So without this, you need a heck of a lot of understanding of what you're looking at and a lot of knowledge, and this helps remove some of that need. So just to give an example of where that's useful, we've got sort of a case study of where we had one sequence where we actually measured a 9 Dalton difference, which Unify can confirm for us through the modification that it's a substitution. But as you can see there's multiple places where, or sites where, that substitution could have taken place, and you can see that if you start to enter in the sequence, you can see if we substitute the A, the sequence stops quite early on, but where it is a T highlighted with the yellow, you can see we've got the full sequence coverage, so it can confirm us at which point the sort of synthesis has failed. So in summary, hopefully what you've seen from Emma and then from me is that the addition of base spray gives us benefits for processing oligonucleotides. We've had Maxent1 for a long time, which is good for your intact protein. Oligos are a little bit smaller, so it was always it worked, but it didn't work perfectly. And what we've seen is where you've got a wide sort of dynamic range of compounds sort of co-eluting. If you can't get total separation, there are clear improvements with base spray at identifying the main product and the low-level impurities at the same time, and giving accurate deconvolution sort of intensities as well, which is a key thing. So we've got a good oligonucleotide solution. We've got sort of validated quite a range of our instruments depending on what your analytical challenges are. We have set columns which we test in-house before they get sent out, so we know that they are working perfectly with the OST standards. We have standards we can provide. We have an on-site support team who would visit and help set up this application, so we're doing everything we possibly can to help ensure your success with this. We've put together a number of guides which you'll see on the website for troubleshooting and method development workflow, and Waters Connect can provide a compliant ready solution for both large-scale batch analysis and the more in-depth characterization when that's needed. And yeah, as I think Stefan also mentioned previously, on our website we've got quite a lot of collateral on there. And with that, I will hand back to Sasha.